Alright guys, so this is the third video for our Flip the Classroom lesson on graphing the other four trig functions. In this video we're going to talk about graphing transformations, and we're going to say that we're going to be able to graph the transformations of cosecant, secant, tan, and cotan in the same way that we graph the transformations for sine and cosine. And basically what this sort of comes to is we know that however many times we rotate around, right, the unit circle, we're really sort of defining our ratio with those same x and y values for each cycle. So what we're going to be able to do is define one cycle, right, define what our trig function looks like in one cycle or one period on the graph, and then just repeat that period over and over again, because we know that these functions are cyclic, which means that they're going to be basically periods that repeat. So right here what we're going to do is define one period for cosecant, secant, tan, and cotan by its quarters, the same way we did for sine and cosine, and then we're going to talk about transforming that one period and then repeating that period, that transformed period, over and over to get the graphs of these trig functions. So right here we know that a period for cosecant is going to extend one length of 2 pi on the graph, right? So we can say that right here, a period of cosecant of x is going to start at the origin, and that means that we start at a vertical asymptote for cosecant. In our first quarter, pi over 2, we're going to see a min, and at the halfway point, pi, we're going to see a vertical asymptote again. Third quarter, we're going to see a local max, and that's happening at 3/2 pi for our period of 2 pi. So this is going to be a max. And then finally, right here, we are going to end on a vertical asymptote again at 2 pi. So that's what one period of cosecant looks like. And one thing that we can sort of think here is that really what we're seeing is this looping behavior between these vertical asymptotes. So we loop down to a min in the first half, and then we loop up to a max in the second half, right? And that's sort of what these mins and maxes are going to be when we graph this. Another way that we can see the graph of cosecant, if we graph the reciprocal trig function, which of course is sine, we see a graph, a wave that looks something like this, and we can sort of see that really the cosecant function is a reflection of the sine function across its extrema. And when we say reflection, basically what we're talking about is we're sort of seeing a reciprocal or inverted image, right? Where the zeros of the sine function are vertical asymptotes, the maxes of the sine function are the mins for the cosecant, and the mins for the sine function are the maxes for the cosecant. So that's one way that sort of people are able to sort of reference the reciprocal sine function and sort of get an idea of what their cosecant graph should be. But what we're going to do is basically this breakdown of the quarters for our cosecant graph. And we're going to do the same thing for secant. So right here, looking at one period of secant, we're going to start at 0 and go to 2 pi, right? And so right here we can say that for a period of secant x, we know we are going to start at the origin. We start right here at a min. In the first quarter, we get a vertical asymptote, and that happens at pi over 2 for our period of 2 pi, but we're going to see that change with horizontal strengths and stretches and phase shifts. So right here we got a vertical asymptote, and then right here, halfway point, we have a max. The third quarter, that's 3/2 pi. We've got a vertical asymptote again, and a period of secant ends back on a min. And again, when we talk about these maxes and mins, we're basically sort of seeing it as looping behavior between those vertical asymptotes, down to a min and then up to a max and down to a min. So right here, that's one period of secant, and just like the relationship that cosecant has with sine, secant has that same relationship with cosine. So if we were to sort of graph one period of cosine, again, we can sort of see this graph as almost a reflection across its extrema, right? There's one period of the cosine wave, and we're seeing the maxes of the cosine be the mins of the secant, the mins of the cosine being the maxes of the secant, and the zeros of cosine being vertical asymptotes. So another way we can sort of think about that. So these are what one period is going to look like for cosecant and secant. And what we're going to do now is talk about how to graph these periods with the same transformations that we saw before. So right here, just like with sine and cosine, we're going to see all of the same additions, subtractions, and multiplications result in the same basically transformations for our graphs of secant and cosecant that we saw for sine and cosine. So right here, a multiplication outside the trig function is going to affect the amplitude, and that's a vertical stretch or shrink. Right? And a multiplication inside the trig function is going to be affect our period, and that's because it's a horizontal stretch or shrink. So same relationship that we saw before with our multiplication inside and outside the function. We're going to see the same relationship that we saw before with the addition inside and outside the function. An addition outside the function is going to affect our line of equilibrium, right? That's basically what we're sort of seeing our trig function oscillate above and below. And an addition or subtraction inside the function is going to affect where we start the period, and that's going to be a phase shift. So basically that's going to affect how the period is orientated on the x-axis. So looking at these, we can basically look at our first function here, which is 3/2 secant of 2x. And when we're looking at this guy, basically what we want to see is that we've got an amplitude of 3/2, and of course a period right here of 2 pi divided by 2, or just pi, right? That means that for the graph of secant, we are going to see our extrema happen at 3/2, or 1.5 instead of 1, and negative 3/2 instead of negative 1, right? So we'll see those mins at 1.5 and those maxes at negative 1.5. We can say that we're going to see an entire period happen in pi, right? And right here, we can just sort of mark off the things that we know are going to happen for our secant function. So right here, when we're talking about secant, we know that we see vertical asymptotes at the quarter periods. So we'll be able to sort of mark off those vertical asymptotes. And we know that we see our functions start at that min, and we see halfway that max, and then we end at that min again. And we remember that secant is that sort of looping behavior. So we're seeing that min, and then we go up into our vertical asymptote, and then between our two vertical asymptotes, we come up to that max, and then at the end of our period in that last quarter, we come down from the vertical asymptote and hit that min again. Now right here, I could graph another period pretty quickly, right? I know that my quarters are going to be vertical asymptotes. and then I know that I'm starting at that min, going up to that vertical asymptote. Then I've got the max halfway, and then I hit that min at the end of my period again, right? And we could just continue on graphing periods of our 3 halves secant 2x in this same way, just marking off intervals of pi and drawing the period in those intervals. All right, so looking at our b right here, we've got negative cosecant of x minus pi minus 1. So we've got a bunch of rigid transformations here. We know that that negative means that we're going to see a flip of the cosecant function. So instead of us having a max, or a min rather, at that first quarter, we're going to have a max at that first quarter, looping up to that max, and our min is going to happen at the third quarter. The rest of the transformations we would see concerning amplitude and period are really going to be unchanged. We're going to see the same amplitude and period that we normally would, but they're going to be shifted a little bit by that subtraction of pi inside our cosecant and that subtraction of 1 outside. So right here we've still got an amplitude of 1. We're going to go up to 1 and down to 1, or we're going to see extremo 1 away from the 1 up and 1 down from that line of equilibrium, and our period is going to be 2 pi, right? So right here, first let's talk about this subtraction of 1. We know that that's going to affect our line of equilibrium, so instead of our line of equilibrium happening at the positive x-axis, we know it's now going to happen at negative 1, right? And the next thing we're going to see is that subtraction of pi shift us horizontally. We know that a subtraction inside the function is going to be a horizontal shift in the opposite direction, so we can say now that our period is going to start at pi, which means that we're going to see a full period between pi and 3 pi, because that's a length of 2 pi on the x-axis. So right here, we can go ahead and mark off the things that we're going to see from negative cosecant. So right here we know that cosecant starts at a vertical asymptote, and it's got vertical asymptote at integer increments of pi. So basically right here we're going to be able to continue to draw integer increments of pi as the vertical asymptotes, and that's because our phase shift is an integer increment of pi. It's basically just 1 pi, right? Now, instead of drawing the min first, right, we're going to draw the max first. Now, right here, with that amplitude of 1, we can say that that means we're going to see our mins happen 1 up from our equilibrium line of negative 1, and our maxes happen 1 down from that line. So right here, basically, we can say that instead of that first min in the quarter, we're going to see a max, and that's again because we've got the negative right there. And then right here in the third quarter, we're going to see the min. And right here we can draw our cosecant function, and it's going to look like this. All right? And we could go ahead and draw more periods of this. We could go back an increment of 2 pi, right, and draw this period again. We know that we're going to see vertical asymptotes at increments of pi, so that's negative pi and 0, right? And then right here we can draw this period again, so we can basically say that we're going to see our period look like max first, and then min. So that would be a graph of our negative cosecant of x minus pi minus 1. Now right here, I want you guys to go ahead and give C a shot on your own. So right here, first thing that we want to do is factor that 1/2 off from the inside of the function. So instead of thinking about graphing cosecant of 1/2 x minus pi over 4, this is going to be cosecant of 1/2 times x, and then this is going to be minus pi over 2. So evaluate that phase shift first of minus pi over 2, and then right here, this 1/2 is going to affect the period from that phase shift. So go ahead and give this a shot. Okay, so looking at this guy, we can say that we know the period is going to start at positive pi over 2, so we can sort of push that up. And we know the period length is going to be pi over 4, and we got that, of course, by taking our 2 pi and dividing it by 1/2, which is a multiplication of the reciprocal, which is going to give us pi over 4. So we had to bump out another 1/2 pi increment on the x-axis to sort of get the full period here. But you guys are savvy, you can do that. So basically right here, we're going to see the cosine graph now right side up instead of upside down. We are going to have a vertical asymptote at the beginning, at the halfway point, and at the end. And we have a min in the first quarter and a max in the third quarter. So this is the graph of one period from our starting point of pi over 2. Our amplitude is 1, so we're not seeing those maxes and mins go up or down any. And we can just sort of graph that one period. And we can also sort of extend it in the opposite direction, right, by basically taking another increment of 2 pi in the opposite direction and graphing that same period again. All right, so that's the graph of cosecant of 1/2 x minus pi over 4. We'll get more practice with these, and what we want to do now is talk a little bit about the graphs of tan and cotan. So right here, we're going to sort of see the same thing we saw before, right? Which is that we know that a period of tan, which happens in an interval of 2 pi, is just going to repeat over and over again. And so what we're going to do is define a period of tan x by its quarters, right? And then we'll be able to sort of map that period out on the x-axis for any transformation, and then just repeat it. So right here we've got the start of tan, and we're going to say it starts at 0, and then the first quarter, right? So we say start at the origin here for just tan x, and right here at the first quarter we're getting a vertical asymptote, and then right here halfway we're getting 0 again, and that's happening at pi for a period of 2 pi. And then third quarter is going to be a vertical asymptote again. And then right here, we're going to end at 0 again, right? So at the end, we're back at 0. Now, remember that when we're sort of mapping this out, really what we're seeing from tan is an increase. So maybe we want to put that in parentheses right here. We know that we're increasing between these vertical asymptotes for a graph of tan. When we go ahead and map out cotan, we're going to want to remember that we're decreasing. So right here, when we map tan out by its quarters, cotan out by its quarters, we can say a period of cotan of x. We know it's going to be decreasing, so we'll want to note that. And then right here we can say that it starts at a vertical asymptote. The first quarter is going to be a 0. Halfway is going to be a vertical asymptote. And again, this is for a length of 2 pi on the x-axis. That's how we're defining a period right now. Brushing this a little bit. Ooh. Line this up a little bit better. We can do that. So right here, the third quarter is going to be 0. And right here, the end is going to be a vertical asymptote. And we know that we are decreasing between these vertical asymptotes, right? So hitting the zeros, the x-intercepts, but decreasing between those asymptotes. This is going to be a little bit easier to graph. So right here, what we'll do is look at one of these guys, and then I will let you guys do the other two. So right here, why don't we take a look at just this first one, and then I'll let you guys go ahead and graph the other two. So right here, we're seeing the graph of tan. We're seeing all the same transformations for tan and cotan that we saw for sine and cosine and secant and cosecant. So that means that multiplication inside is going to affect the period. Multiplication outside is going to affect the amplitude. C is going to affect where we orientate ourselves, or where we start our period on the x-axis or on our line of equilibrium. And D is going to affect that line of equilibrium, basically where we are sort of going up and down from on the y-axis. So right here, we can say that our amplitude for this first guy is 1, and our period for this first guy is going to be 2 pi, right? Nothing multiplied on the inside of our function, nothing multiplied on the outside. Now right here, the only real change that we're seeing is the subtraction of pi over 2, which is going to affect where we start our period, right? So right here, a subtraction inside the function is going to be a horizontal shift in the opposite direction. So that means that we're starting our tan graph now at pi over 2. And that a period is going to be 2 pi from that starting point of pi over 2. So right here we've got one length of pi, 2 lengths of pi, and right here our period is going to end at 2.5 pi. We know that basically we're seeing our vertical asymptotes at the quarters. So we can draw those at the quarters of the period. We start at 0, and we have 0 at the halfway and 0 at the end, and we are increasing between these vertical asymptotes. So starting at 0, we go up into that first vertical asymptote, then coming from negative infinity, we go through 0 again, up into our second vertical asymptote, and then we come from negative infinity, and we end up at 0 right there. Now, you can see that this is a much easier graph to draw. We can sort of just go ahead and finish this piece of the graph. Right here, it looks like we have another 3/4 of a period, which means that we are going to see a vertical asymptote right here at the first quarter, 3 pi, and at the third quarter, 4 pi. And we can go ahead and graph the rest of this tan going into that first vertical asymptote of the second period. And right here we can graph this middle piece again. Right? And you can extend it in the opposite direction as well. So basically right here, if we say that we're seeing now basically our vertical asymptotes at increments of pi, right? Because of this phase shift, we can basically draw out the rest of our graph. And remember that tan is going through the x-axis at its quarters, right? So that's halfway between each vertical asymptote. And it's going to look like this. Now this is a rough sketch, but you guys can see that it's pretty easy to do quickly. So why don't you guys go ahead and give the graph of cotan and tan a shot here. Pause the video and we'll look at this together in a second. Okay, so looking at these last two guys, we've got B. With this graph of cotan, we can see that we have a multiplication of 2/3 on the inside of the function, and basically a multiplication of, we could call it 1 on the outside. So the amplitude is going to be 1. There's no vertical stretch or shrink there. But the period is going to be 3 pi, and that's because we're dividing our pi over 2 by 2/3 pi, which gives us a period length of 3 pi. And so basically what that means is we're going to see an entire period stretch out to 3 pi. The other thing that we're seeing here is a negative in front of, sort of scribbled over that, a negative in front of that cotan, right? And that basically means that we're going to be flipping that cotan function. So whereas cotan would normally be going down between its vertical asymptotes, now because of the flip, it's going to be going up. We know that cotan starts at a vertical asymptote, has zeros at the quarters, and then basically vertical asymptotes at the halves, we might think, right? So start, and then first half vertical asymptote, second half, or the finish of the period vertical asymptote. So right here with that flip, we're basically able to draw cotan as basically going from its first vertical asymptote and then increasing through the 0 at the quarter, right? And we can sort of repeat that backwards. With our next graph, we have two transformations that we want to think about, right? We've got the multiplication of 3 halves, which is a vertical stretch, and then we've got the multiplication of 2 on the inside, which is going to be a horizontal shrink, which is going to change our period to length of pi. So right here, this is actually one entire period for our graph of tan right there. It's not exactly perfect, but you guys get the idea. And basically right here, the vertical stretch is going to be tough to draw. So what we'll do is really just draw the graph of tan and sort of try to lengthen it out a little bit. But right here, basically what we're seeing is our tan function starts at 0. It's got its asymptotes at the quarters, right? And a 0 at halfway, and it finishes at 0. And we know since we're tan, we're going to be increasing between those vertical asymptotes. So starting at 0, we increase between our next 2 vertical asymptotes, crossing at the halfway point at 0, and then right here, increasing to the end of the period at 0. And you can just draw this period again and again. Pretty quickly. And again, you want to be somewhat accurate with how you're getting your zeros there. But so these are the graphs of these functions. It's a little longer than I'd hoped, so I'm going to sort of instruct you guys to fast forward what you can here. And we will do a worksheet on Wednesday. Okay, guys, I'll see you Wednesday.